Hi, good morning. And I'm sort of hoping that guys can hear me okay. The reason I say that is because I'm on a slightly different computer. I'm obviously in a hotel room, so I'm sort of relying on all the technology to work completely fine. So I've just done a quick check, and I think it's all working. So yes, well, I say on this slide today is the 19th of December, the 9th of December. That's actually wrong. Today is the 16th of December. But every week we do let's say, webinar for our members of our ZP Developer Zone, and we're just doing that, let's say, webinar now. I just want to say hi to Tarun because I can see that he's come online, so nice to see you. And let me jump into it. Like I say, it's a little bit more jumpy today because I'm dealing with different IT systems, so I hope everything's working okay. All right, cool. All right, so every week we do the ZP Developer Zone. We have our academy, we have our webinars, which you're attending. We have our collaborations. I want to say that one of our ZP Developer Zone members we spoke to him this week, and we're arranging for him to now do a sabbatical with us for 3 months. He has been following us, to be fair, for over 2 years, even before there was a ZP Developer Zone. So he's going to be coming to us hopefully in about April next year. And then we have job offers, and then we also have our actual ZP Developer Zone website. So let me jump into it. We're also going to do a workshop. I was a bit hesitant on the workshop because I was wondering how this coronavirus was going to go, and it's not going too well. So I'm really sorry for everyone. Face-to-face meetings looked like they were coming up, but now they look like, unfortunately, they're sort of becoming less again. So every week we use the forum to answer questions, and I feel like I'm going a bit slow, so let me jump into a couple of the questions. So one of the questions, I think this might be interesting to Tarun because he has an interest in sort of bioelectrochemistry. So let me jump into it. So one of the questions is somebody's trying to develop a sensor for D-beta hydroxybutyrate. Now I know it doesn't say the word ketone in there, but when people are generally testing for dehydroxybutyrate, they're generally interested in making a ketone sensor. Now, ketones the measurement of ketones is very interesting to diabetics. It's not as well known as testing for glucose for diabetics, but I also think that ketones has become sort of more interesting because of people interested in understanding the effects of their diet. So in this question, they say, I want to develop a sensor for D-beta hydroxybutyrate, and he's wondering if he can use CNC, carbon nanotubes, or graphite paste mixed with 110 phenanthroline 5,6-dione. Now, the good news about this, let's say, presentation today is I do have experience of dehydroxybutyrate. I do have experience of CNTs. I also have experience with, obviously, graphite paste and also 110 phenanthroline 5,6-dione. That's why I can say 110 phenanthroline 5,6-dione so well, because actually I have used it a lot in my own, well, not a lot, but I have used it in my own career. I'm also very familiar with NADH. This is obviously one of the cofactors to support dehydrogenase enzymes. So I appreciate all the questioning. I understand why you're asking this, and that'll be one of the questions that we'll deal with today, is how to make, essentially, sensors for ketones or dehydroxybutyrate. Question number 2 is somebody is interested in our needle patches. These needle patches are on our website, or these microneedle patches, and they essentially are designed to put microneedles through the skin. They're interested in glucose, which I think is a lot of people are interested in glucose these days on microneedles. I've mentioned it for a few weeks now, that BioLink is in San Diego. They've been funded to like $100 million US, and I think there's even another company in San Francisco that's also been funded to $100 million. And they're also interested in cortisol. And cortisol is a lot of people are interested in cortisol in sweat, and I genuinely believe that the only people who actually have a commercial system for cortisol is actually us at the moment. And I know it's hard because it took us a long time. So the first question is, the inquirer is asking, how do I make a sort of ketone sensor? it's worth saying that we've actually do have a ketone sensor. So I will talk about how you make your ketone sensor, but we can talk with some experience on this because we do generally have a ketone sensor. So and it's also probably worth saying that we also have a what I call an NADH sensitive electrode. So NADH is not normally oxidizable so readily on, or is not electrochemically active on gold and platinum and carbon. I think it has quite a high over potential, and when you do detect it, it ends up fouling the electrode. So it's just to say that when I speak about this morning, it is coming from a position that we actually have a ketone sensor, and we also have an NADH sensitive electrode as well. Now, the inquirer is asking, can they use this 110 phenanthroline 5,6 dione in their carbon paste to detect graphite? Obviously, they've done their homework, the inquirer, and yes, you can. Obviously, this kind of molecule, this kind of quinone structure is, reduced to a quinol, and you can electrochemically, reoxidize that quinol back to a quinone, and you can do it on things like screen printed electrodes. So, fundamentally, this kind of mechanism where NADH reacts with, I would say, the mediator in this case. The mediator is reduced, and you could then use the sort of oxidation of the reduced mediator to kind of detect the fact that there was NADH in there. This mechanism is well known in the literature. I've worked on this kind of work myself, and I'm pretty sure I'm not pretty sure. I absolutely am sure, because this is what we're doing similar things ourselves at Zimmer and Peacock. You can do on our hypervalue electrodes as well. So obviously I can say that because, we do have an NADH sensor, we do have that ketone sensor. So yeah, this hypervalue carbon electrode will do a good job for you. So that's the mechanism, just to kind of get a sense of what's actually going on here. Now, one other kind of, I just want to make some comments about graphite really. Graphite, to some degree, can actually probably react with NADH. I'll show you some literature precedents for that. But, I always feel a bit embarrassed to sort of, say this kind of stuff in front, because a lot of the guys who come to these webinars, they have their PhDs, in the various subjects. So I know people know this, but, graphite is actually, it's obviously a sheet of essentially rings, carbon rings, but actually on the edges of it, the carbon is oxidized, and you have kind of carboxylic acids, you have lactones and lactols and phenols and hydrides and pyrones and ethers. You also have quinones, and it's probably worth noting that, those kind of quinones are very similar to the quinone in this 110 phenanthroline 5,6 dione here. And so the reason I sort of say this is, if you've got a graphite, it might inherently have activity towards NADH. You probably have to enhance its activity to NADH to get a decent signal, but inherently it will have some quinones in it. And if you do a little sort of test with NADH, you'll probably find that the signal increases because NADH will react with these quinones, make them quinols, and then you can reoxidize those in a sort of voltammetric experiment. So the inquirer is kind of asking, should I use carbon nanotubes? Yeah, I think carbon nanotubes will work, especially if they're sort of partially oxidized and you've got these kind of quinones on there. Should I use graphite paste? Yeah, you should use it because I think graphite doesn't actually have these quinones in it. Should you add the 110 phenanthroline 5,6 dione or the PD straight into the graphite? I don't think it's absolutely necessary. I mean, if you mix this mediator in with the graphite and then sort of print it, yeah, you might get a few extra quinone groups sticking out the surface, but I'm not sure that's really 100% required in order to get essentially a functionalized quinone surface. But you can try it. It'll look like it's working, but it's probably working more likely because you've actually got inherent quinones in the graphite, not because you added more quinones from your mediator. Now, I obviously did a quick Google on this. I mean, and just want to kind of say, CNTs, carbon nanotubes. There's a paper here, and this paper is by Richard Compton, who's at the University of Oxford. I know Richard very well. His work is always, world class. And then this is one of his really good students, who's a professor in his own right now, Craig Banks. I know Craig by reputation. I haven't met him, but I know these two guys. So when they kind of, say that, the electrocatalysis, let's say, of NADH using carbon nanotubes and carbon nanotubes, and they say, pyrolytic graphite, yeah, then their work is good quality, and this is genuine stuff. Like, say, you can believe this kind of thing, and so they quite clearly show that actually I know they're saying edge plane pyrolytic graphite here. I think when people say sort of edge plane pyrolytic graphite, we sometimes kind of mean glassy carbon, but they're just showing that it does work, that it's reacting towards NADH. So I do think that putting the mediator, the PD, into the graphite paste, I think that's a slight overkill. They didn't do this in these papers. They were either using carbon nanotubes or glassy carbon, and they were convinced that it was reacting with NADH. And I would essentially agree with them that that would have been my expectation. And so I independently would have had that thought, and then obviously it's confirmed by the literature as well. But my sort of take on all of this is, if you want to make, let's say, a ketone sensor, then the first thing you need to do is make a electrode that's sensitive to NADH. So, my kind of philosophy on most things actually is really start simple. So start with the idea that you're going to take a, let's say, a hypervalue ZP electrode and test as is. So I literally just mean do some cyclovoltammetry with NADH on that, and just see if you get a voltammetry that persuades you that NADH is there. I just want to say a quick hi to Hitcham, who's come online this morning. So good morning, Hitcham. Nice to see you. So my philosophy is, don't get too complicated too quick. You want to detect in the first instance NADH, because I ultimately want to build a ketone sensor. Graphite, yes, it does look like it works. The only thing about the papers, let's say from Richard, were a lot of that work was done on glassy carbon, and glassy carbon or edge plane pyrolytic graphite is not an easy material to manufacture with. So I would say start off simple. Get a screen printed graphite electrode, carbon electrode, which are often just graphite, and test it with NADH. I've got a slide in a bit that'll explain that a bit, but test as is. The reason being is my hypothesis is that graphite already has quinones in it, and if you get the right kind of carbon ink or carbon paste from the right manufacturer, then it might have a lot of quinones on it. Now, if you test it and you think, I might have some NADH activity, but it's not enough, then I'm going to say oxidize the electrode. So I've just made this up because I haven't actually done this myself, but I'm sort of saying, you could put like 1 volt onto that electrode for something like 20 seconds just to oxidize the surface up a bit, so that you turn more of the edge into quinones and into these oxidized states than would have otherwise been present there. So don't start formulating inks, because it sort of delays your development or your research. Get something off the shelf, test it. If it shows a little bit of activity but not enough, then I actually say just oxidize those. And so I'll give you some conditions here that there's an educated guess, that 1 volt, 20 seconds should be enough to kind of oxidize the surface. Another thing you can then do is, if the papers of Richard are correct, then what you could actually do is, if you're not getting enough activity from the intrinsic graphite, oxidize it. If that doesn't look like it's working too well, drop cast some carbon nanotubes onto the surface. I'm pretty certain that in lots of Richard's papers, he does a drop casting of carbon nanotubes. So take the electron and drop cast carbon nanotubes onto it. When I say drop cast onto it, take an electrode. I just put something like 3 dots on it like this. We do it with a sort of micro pipettes, and then just blend the 3 dots together, and that should be enough to get carbon nanotubes, and then you should have a sort of graphite bed with carbon nanotubes essentially sort of absorbed onto the surface of that. And then try that. Then you're getting pretty close to those Richard Compton papers. I'm just going to say also, if you want to make a ketone sensor, I'm absolutely certain that what you can actually do is just have, you could drop cast, for example, the mediator onto the electrode and dry it. And when you add your sample, then the mediator will redissolve into the sample, and that should work as well. So you didn't necessarily have to modify the carbon. You could actually just drop cast the mediator onto the electrode, dry it, and then when you add a sample, then it could redissolve, and then you've got your mediator in position, and then you could detect your NADH. I'm just going to talk about EC reactions a little bit. So what I mean by EC reactions, this is a nomenclature that says you can have a reaction that's electrochemical and then followed by a chemical reaction. So let me sort of explain that a bit. So let's say I was trying to investigate whether I had activity with NADH. I could do the cyclovoltammetry of the quinone, and I would get, hopefully an oxidation or reduction wave. And I would do that obviously on a carbon electrode. Now, in the presence of NADH, the CV should change. Now, you've got to play with the scan rate a bit. If you do a very fast scan rate, you do the electrochemistry so fast that you don't actually see the resulting chemical reaction. But as you slow the scan rate down, then you'll see the effects of the chemical reaction. So if you don't see any effects or any difference from doing a reaction with phenanthroline, if you're doing the electrochemistry of phenanthroline 5,6-dione on a carbon electrode, you get nice CVs, and then you add NADH and you don't get any change, it's probably because you're scanning too fast, so turn down the scan rate. The reason that the scan changes is because what you're doing is you'll notice that one of the biggest changes is you don't have your reduction wave anymore. And the reason you don't have your reduction wave is because you have already chemically reduced all of the quinone down to the quinol. And so there's no, in fact, I might even have you already did that reaction. So there's nothing to reduce because you're chemically already done the job. So this is just to sort of say that I would say that one of the best ways of making your ketone sensor with the mediator that you have is taking a screen printed carbon electrode, drop coat the mediator down onto it, get a CV for it so you get a sense that that's working, and then just add in NADH, and it should change from being a clear oxidation reduction wave to maybe just the oxidation wave. And the reason the reduction wave disappeared is because you've already chemically reduced all of the quinone to quinol, and this is called an E reaction because you're just looking at electrochemistry, and when you've got the presence of NADH, it's electrochemistry followed by chemistry, and they just call that an EC reaction. I don't want to get into lots of nomenclature with you, but I just thought it would be kind of interesting. I'm looking at the time now, and that's 20 minutes on one question, so I just want to say hi to Aftab, who's come online this morning. So nice to see you, Aftab. See, I'm in a hotel, so I was sort of slightly winging it this morning, guys, because not winging it, but I don't have all my IT with me. So making a mediated sensor, my suggestion is take the carbon electrode, drop coat down your mediator, spread it with a pipette tip, let it dry, and that should do it. I'm just going to do next question. So the gentleman or the inquirer is interested in a microneedle patch. So we have these microneedle patches. On our website, we have the calcium sensor and the lactate sensor data. We also have glucose data. Sorry, it's really blurry. But let me just quickly summarize what we're looking at here. What we're looking at here is Zimmer Peacock have these microneedles. We functionalized it with the enzyme for glucose. And this is at 0 millimolar. So we have about 12.5 microamps at 0 millimolar. This is 5 millimolar, so the current's jumped up to about 20. This is at 10 millimolar, so the current's jumped up to 23, 24 microamps. This is 15, so we're at about 26 microamps, and this is 20, and we're getting to about 27. So the inquirer is interested in information regarding our glucose microneedle patch, and the answer is we have it. It has what I would call a standard connector here, so you can use this on a lot of potentiostats, the Sense It Smart, the Easy Flex from ZP, the Anapot. You can use this on a number of potentiostats, and this is the data that we have. This sort of shows you that we have a certain amount of linearity, not the world's best linearity, but it does actually function. And this data and this picture here shows that we're testing it in vitro. So I just want to do a quick summary and say so thanks to Tarun for coming on, Hitcham's here and Aftab's here. I'm just reading something that Hitcham said. Hitcham saying that drop casting is good for potentially for prototyping, but I agree. It's drop casting is good for prototyping. It's not always something. It's not always ideal to get the best signal, but at least give you a sense of what's is it going to work or not working. So in this question, yeah, we do have a glucose microneedle patch. Essentially, here's the data. What we'd say to people is if you're interested in it, you have to buy them and try them in your application. Now, the next question is, he's very interested in our cortisol sensor, and he wanted some details about the cortisol sensor. So the cortisol sensor, I actually think, is unique. I think we're the only people in the world that actually make a commercial cortisol sensor. But what we're doing is we're not putting it on the open market. We're only using it now with people actually in projects. So at the moment, we're only using it with projects. So we have a few big clients at the moment that are using the cortisol sensor in their applications, and we're very happy for them. So unfortunately, to get access to the glucose sensor, just go to the website. But if you want the cortisol sensor, then you generally have to get into quite a sizable project with ZP in order to access the cortisol sensor. So I'm just looking at the time. Yeah, it's 25 past. So let me just do a sort of quick summary. So we did have this question this week about how to make a ketone sensor. I think I did speak too long on it, and I apologize for that. But we can see we have a fair amount of knowledge at ZP about NADH, about graphite, about carbon nanotubes, and even about phenanthrene dione. And then we also do have the glucose microneedle patch available on our website. I showed you some data from it. I explained the responses to glucose in the sort of 0 to 20 millimolar concentration, which is what's required. And we do have a cortisol sensor as well, but that one we're only making it available through projects. So I know I said it at the beginning, but I'll say it at the end that one of our ZP Developers Zone members will be joining us for a 3-month placement in April, and so I look forward to welcoming them then. I appreciate you guys coming along this morning, and I will just say thanks very much, and I will catch you soon. All right, take care, guys. Bye-bye.